Hi there, how's it going? Terry Brown, Mechanical Engineering here with another video lecture, this time looking at mechanisms. So let's get into it. Let me share my screen. And all right, so most of what I'm going to go through in this lecture comes from the textbook Design and Analysis of Mechanisms by Michael Ryder. If you're at UTS, then you've got free access to the textbook, and also another one by Waldron. And the links to those are in the subject's Canvas site. So I encourage you to check those out. But anyway, let's get into the lecture. All right, so most of what we will look at is 4-bar linkages. So you may or may not have come across 4-bar linkages before. Talking to students in the 2 classes this week. The first class where we had, I don't know, 15, 20 people, I guess, nobody really had heard about 4-bar linkages. And then in the second class, there was maybe 1 or 2 that were, but yeah, so a 4-bar linkage, if you look in the little image of me on the side there, you can see I've got a little Meccano model showing a 4-bar linkage. So often when 4-bar linkages are drawn, you can only see 3 links. So the fourth, so like this one here in the top left-hand corner of this picture, and yeah, so the fourth link is ground. Right? So we always include ground in our in determining how many links there are in a linkage. All right, so with respect to 4-bar linkages like this, we have 3 main categories. Firstly is function generation. So we might have an input like I've got here from my right hand. And then we've got some kind of desired output on the other side. Right? Usually you would have this link rotating all the way around, and then this one will rock. So we call that a crank rocker. So if this link here can rotate 360 degrees, we call that a crank. And then this one here just rocks backwards and forwards. So we call that the rocker link. So yeah, that's usually what we have. But we could have something that just rocks backwards and forwards here, and you get some desired output on the other side. Then we have path generation. So we have this coupler link. Right? So we usually have the ground link, you know, 2 side links here, and then this is called the coupler link. Right? So usually what we have in path generation is that there's a point on that coupler link that we desire to move in a particular path. And actually, let me just click on through the PowerPoint. So yeah, we just talked about there. So here we're not interested in any particular point on the coupler link or the function generation. We're only worried about what's happening on the output link here. Okay, so then yeah, we've got path generation. So the typical or some examples of how that might be applied is in indexing here. So we're generating a rotating indexing component. So as this rotates around, this would move. So if we had it like, whoops, I've gone off the screen. So if we have something like that, and this coupler link moves, then there's a point on there that we want to follow a certain path. So here it's rotating this around in stages. What's that, 90 degrees at a time? Or we might have, so you can see on the right-hand side of this dashed line here, it's kind of approximately straight. So another application of this is to index something along in a straight line. So, if we had the thing that we want to move over here, right, we'd need to rearrange things or make sure we didn't have things running into each other. But if we wanted to move something along in a straight line a little way and then move it along a little bit again as this goes around and around. And a typical example of application for that would be in an old-fashioned film advance mechanism, right, where you had holes on either side of the film, and there'd be a little pickup point on the link that would grab that and move it along. Okay, and then the most general case is motion generation, where the entire motion of the coupler link is important in the mechanism. So in the example from the textbook, we've just got this box coming along a conveyor, and then this mechanism timed to receive the box, lift it up and put it onto the next thing. Before we had electronics and electronic actuators and things like that, and programming, then this kind of mechanical mechanism was used a lot more. But these days with, as I said, mechatronics and electronics and programming, we can do a lot of this much more flexibly and simply than with a mechanism like this. But nevertheless, these are still in use and still worth knowing about as a mechanical and or mechatronic engineer. And that's what we're going to look at today. So other examples or practical applications for motion generation. So the first one here I've got is for vehicle suspension. So if you look at just one side of the car, so this is looking at the front or the back of the car, and we've got double wishbone or double A-arm suspension. All right, so this is what it, down in the bottom left-hand corner, this is what it actually looks like. So the yellow bits form the moving links of the 4-bar mechanism, and the chassis of the vehicle is the ground link, if you like. Right? So, and it's important that when you design your suspension system, that the motion of the upright and the wheel, which is the coupler link in this version of the 4-bar mechanism, right, has the correct motion and orientation, right? Because that affects the camber angle of the wheel and tire, right? Which then of course affects your contact patch, which then of course affects your grip and so on, right? All right, another example would be the tilting garage door. Right, so here we want the garage door to be just a single piece, right? And that whole door would move with this mechanism. So the 4-bar mechanism here, so ground would be this bracket attached to the wall of the garage. Then we've got, let's call this the input link. Then the door is the coupler link, and then this is the output link. All right, it's not really output link, but yeah. So ground link here, and then this is your coupler link, and that's the motion that we want to control. So we want this door to be able to be horizontal at the top and then be able to come down and be vertical to close the door. But right, the back end of as we rotate this, so if we had something moving like that, we don't want the top or the back of or the top of the door there to hit the roof of the garage. All right, another example here of this is a kitchen door cabinet. If you're at home, you can stop the video and go and have a look in your kitchen cabinet. If you're somewhere else, then have a look when you go home and see if you can see a mechanism that looks something like this. Right? So this is looking down from the top of the cabinet, looking at the top of the door, and inside the cabinet is here. So when we're designing mechanisms, typically we'll start with what we call a kinematic diagram, which is just lines and points. Okay, so similar to a circuit diagram when you're designing an electric circuit, or also similar to your free body diagram that we did previously in engineering mechanics. So you can see here I've created a SolidWorks model just in Sketch. So when I create my kinematic diagrams, typically I'll do it in SolidWorks, so that then I can move things around and see how the mechanism moves. All right, so just some words here just to explain what it's all about. So the stick figure representation of the linkage, first step in designing or analyzing mechanical linkage, shows the relative motion. In a static drawing like this, you can't really tell much, and but it does tell you what the relative motion is between them, right? So, but if you want to get a better picture of what's actually going to happen, how the mechanism is going to move, then create a SolidWorks or whatever software you're most familiar with, model that you can do that with. Okay, made up of nodes and straight lines. As I said, it serves a similar purpose to an electrical circuit schematic. All right, so we've got some terminology that we need to be aware of and make use of. So a link is a rigid body with at least 2 nodes, and a node is a point on a link that attaches to another link or can attach to another link. And when we connect 2 links together, that forms a joint. Okay, and the 2 most common joints are, well, at least in 2D anyway, so we're just going to keep our analysis to planar mechanisms, are pin joints and sliding joints. Okay, so my 4-bar mechanism here has 4 pin joints. If I had a slot in here, then put the bolt through the slot, then I would have a sliding joint here. Right? And we would represent that, something like this in our diagram. So links categorized by the number of joints that we have. So binary link has 2, ternary link has 3, quaternary has 4, and so on. All right, if we have 3 links connected at a point, then the joint is considered, or the point is considered to have 2 joints here. Okay. So when you're counting up the number of joints, as we will do shortly in some examples, if there's 3 links connected at a point, then there are 2 joints at that location. So they were full joints. Half joints have 2 degrees of freedom. Okay? So a full joint has only 1 degree of freedom. So here at my pin connection, only rotation degree of freedom is possible between the 2 links, right? It can't move relative in a translational way, right? So there's only 1 degree of freedom there. If I'd put a slot in the link here and put the pin in the slot, I'd be able to slide the pin in the slot and also rotate in that slot. So that would have 2 degrees of freedom. So that would be considered to be a half joint. So 2 other common half joints are a cam, so just something on a surface. So it's constrained to move along this surface. So it can't move off the surface. So 1 degree of freedom, translation in the horizontal direction, and then a rotational degree of freedom. Okay, remember it's the relative to the 2 surfaces. So even though this body will be moving up and down, right, the cam follower will move up and down, right? It's the relative motion between the 2 bodies that's important. Right? And similarly with gears. So it can translate along, but it also can rotate on that surface. Okay, in our kinematic diagrams, we have numbering and lettering conventions. They're all listed there for you. I'm not going to read all those out for the sake of time. You can read those and refer to those as necessary. Right. One important concept, or one of the important concepts that you need to understand when analyzing and designing mechanisms is the degrees of freedom or the mobility of the entire assembly of links, right? Or the mechanism. Okay. So when we put all of our links together, like I've got here in my little 4-bar mechanism, look at me on the side here, in order to make all of those links move in a predictable way, right, I only need to put in one input. Right? Okay, so this 4-bar mechanism has a mobility of 1. Okay? If I undid this, right, and I moved in fact, let me quickly do that. I'm going to just take this apart just quickly. All right, if I do this, then the other parts are free to do whatever they want. Right? So there's more than one degree of freedom in this linkage. Right? Because I need more than one input to control what's happening with all of the links. Right? So in analyzing and designing mechanisms, we have a way of working that out without building models or physical models like I've got in my hand here, or like I've got in my SOLIDWORKS sketch, and that is to use, firstly, Kutzbach's criterion, and this is simplified for 2D planar linkages. There is a Kutzbach's criterion for 3-dimensional linkages, but we're just going to look at the 2D in this lecture. Right, and Kutzbach's criterion says that if we count up the number of links, including the ground link, and we count the number of 1 degree of freedom joints or full joints in the linkage, and we count the number of 2 degree of freedom joints or half joints in the linkage, and put it into this equation, then that will tell us the mobility or the total number of degrees of freedom for the mechanism. Okay, so let's do that for the 4-bar mechanism. So here we have number of links is 4, 1, 2, 3, 4, including ground. Number of joints is 1, 2, 3, 4. Number of half joints is 0. So if we put all of that into Kutzbach's criterion, we get a mobility of 1, right? Which is what we know for a 4-bar mechanism, right? So mobility of 1 says it has total degree of freedom of 1. We only need 1 input to control that mechanism. And slider crank mechanism, we do the same thing. So count up our links. We've got ground, 2, 3. The 4th link is the slider. The number of full joints, we've got 1 pin joint here, 2, 3 pin joints plus 1 slider joint, which here is considered to be a full joint because there's only the 1 degree of freedom, right? It can only move horizontally backwards and forwards. Right? Okay, so if you put those numbers, right, it's the same numbers, so obviously you're going to get the same mobility for the crank slider or the slider crank mechanism. Okay, the other way we can count the degrees of freedom or determine the mobility of the mechanism is by using Grubler's equation. Right, so with that, we just count the number of different types of links in the mechanism, and this one, as you'll see, doesn't obviously work all the time. All right, so but if we do for a 4-bar mechanism like this, we've got 4 binary links, okay, and 0 other links. So if we put that into Grubler's equation, then we get a mobility of 1. All right, what about if we do a 3-bar truss? What are we going to get? Okay, let's use Kutzbach's criterion. So hopefully you can guess or think what the mobility might be. Right, so hopefully you know that it's not actually a mechanism. Right? This is going to be a structure, right? So a triangle, 3 links connected together like this to form a triangle, can't move. So I've got one here. Right, so I've got 3 links connected, 1, 2, 3, and aside from it, the little bit of play in the clearance where the bolts go through the holes, right, that's the structure, right? I can't move the links relative to each other. Yeah. All right, so let's do the counting. So number of links including ground. Right, so I've shown here right, a third link as the ground link, same as I did with my 4-bar mechanism, right? But I could draw that without this bottom link here shown and just draw it like this, right? So my body becomes, if I don't move my fingers, becomes ground, right? I don't need the link in between, right? So same here, right? One of these links is considered to be the ground link, right? So we have 3, number of 1 degree of freedom joints. We have 3, no half joints. Put that into Kutzbach's criterion and we get 0. Okay, so that tells us we have a structure that's statically determinate. Okay. If we get -1, then we'd get a structure that's statically indeterminate of degree 1. So if you're not sure what static determinacy and indeterminacy means, go back and look at your engineering mechanics that we did a couple of years ago. All right, so it's not a mechanism, it's a structure, as we know. If we use Grubler's equation, we get 0 as well. Okay, what about if we do this? Okay, again, we should be able to see this and say, yeah, that's a structure. We know that it's what we use to build a truss. But let's apply Kutzbach's criterion anyway. So stop the video and have a go at doing that for yourself before I go through it. All right, hopefully you've come back from having had a go at doing that for yourself. Just make sure you write down the numbers. Don't just have some waffly number in your head. Oh, I think it might be that. Oh, I'm not sure. Actually write down a number and commit to it. All right, so number of links including ground, I counted 5. So 1, 2, 3, 4, 5 links. How many joints do we have? Now, some of you may have had 4. Let's see what I've got. I've got 6. So why have I got 6? So if you've got 4 and I've got 6, stop and think about why we've got different answers. Okay, hopefully you've stopped the video and had a thought about it, maybe gone back to some of the previous slides. All right, so what's happening here? Right, we've got more than 2 links connected. Right, so we've got 1, 2, 3 links connected at the same point. So here we've got 2 joints. And here we've got 2 joints. So our total is 1 plus 1 plus 2 plus 2 gives us 6. No half joints. So if we put that into Kutzbach's criterion, we get 0 again, as we expect. So if we do the same thing with Grubler's equation, we've got number of binary links is 1, 2, 3, 4, 5. 2, 3, 4, 5, yeah. No quaternary links. And we put that into Grubler's equation, and that tells us we've got a mobility of 2, which is obviously not correct. All right, so, and if you think about it, right, you could treat either one or the other of these 2 triangles as just a single binary link. Right? So it doesn't matter if we make our triangle with three pieces like this, or our triangle is made like this, right? If you look in the picture, right, video of me on the side there, right? So I've got a triangle, right? You could have it like that, right? Then this point here is just part of the rigid link, right? Anyway, so this is just to be aware that Grubler's equation, you need to be a bit more careful with how that's used. All right. Okay, and the treating it as a single binary link is what I've just discussed there. All right. All right, so let's look at the door mechanism that we looked at before and use Kutzbach's criterion again. So, which I've put there for you. So count the number of links, including ground. So stop the video and do that. Okay, so how many did you get? I got 6. Now there's possibility that some of you got 10, right? Because you counted 3 links here instead of just 1. Okay, and we'll see what happens if you had done that in a second. But here, right, this link number 2 and link number 3, right, are rigid bodies like this. Right? Look at me in the video. Right. All right, so we've got 6 links. How many joints do we have? How many 1 degree of freedom joints? So I'll give you a second to count those up. Okay, so hopefully you're back and counted the number of 1 degree of freedom joints. I got 7. So you may have got something different. If you did, then stop the video and have a quick think why that might be. All right, so I've got 1, 2, 3, 4, 5, 6, 7. Right? 1 degree of freedom joints. Okay, no half joints, so put that into Grubler's equation and we get a mobility of 1. Okay, and you saw that possibly in the GIF that I showed you about the 3rd or 4th slide, where I had my SolidWorks model, where I could just grab on one point and move the whole thing, and it just all moved together as one. Right? Okay, if we apply Grubler's equation with those numbers, so what have I got here? So got a little bit different here. So number of binary links this time. So the number of links with only 2 nodes, we've only got 4 this time, right? So links 2 and 3 are not binary links. They're ternary links. We've got 3 nodes there, right? So 4 node links, we've got 0. 5 node links, we've got 0. Put that into Grubler's equation and we get a mobility of 1, right? Which is what we expect. All right, so just quickly, if you had have made the mistake of seeing links 2 and 3 as 3 binary links, let's see how that works with Kutzbach's criterion. So number of links including ground, you got 10. So count the number of joints if you think that there are 10 binary links. So I'll stop the video, count up those joints. All right, hopefully you've done that and got a number. So I got 13. Some of you may have got less than that. Right? Why did you get less? Right? Possibly because you forgot to take into account that there are more than 2 links attached at some points. Right? So here we've got 2, so that's 1 joint. Here we've got 3, so there's 2 joints here. Here we've got 3, so that's 2 joints. Here we've got 1, 2, 3, 4, so that's 3 joints. Right? So if you go through and count them all up, we get 13. Number of half joints is 0. Put that into Kutzbach's equation and we get a mobility of 1. right? If we use Grubler's equation, so we've got 10 binary links, right? Same as we had up here. No quaternary links. Put that into Grubler's equation and it doesn't work, right? So yeah, you just need to be careful with that. All right. All right, what about a 5-bar linkage? So here we've got an extra link in between the, so we've got our 4-bar linkage here. We just put an extra link in there. What happens to the criterion, or the mobility rather? Number of links including round. Right? The name gives it away. Number of links is 5. Count up the number of joints. Again, should be pretty easy. We've got 1, 2, 3, 4, 5. No half joints. So put that into Kutzbach's criterion, and we get a mobility of 2, right? Which tells us that we need 2 inputs to fully control the behavior of, or the motion of, this mechanism. Right? If we go to Grubler's equation and do the same thing, number of binary links. Right? So again, we'll have 5 there, no quaternary links, no pentagonal links, and Grubler's equation tells us that we have mobility of 2, which is what we got for Kutzbach's criterion. All right, what about for an open linkage? So again, Kutzbach's criterion. So how many links do we have? Count the number of links. Right. So some of you may have had only 2. Don't forget you need to include ground. Okay, so we have 3 links. Number of 1 degree of freedom joints. We only have 2, right? So this one out here is not connected to anything. So it's a node, but not a joint. 0 half joints, and our mobility is 2. Okay. So in order to fully control this linkage, we need to have something to control the link number 2 and also the link number 5 between links 2 and 5. So again, if I undo my 4-bar mechanism just quickly. Set it up a little bit. Okay, so if I control this one, the other one's just free to do whatever it likes. Okay. And if I loosen that up, that 3rd one out there would also be free to just do whatever it likes, right? And Newton would tell it what to do. Okay. So in terms of kinematic control of the motion, right, we would need to have, so if it was like something like a robot arm, okay, we need to have a motor here, motor at the bottom, motor here, and a motor here at all of those hinge points to control what's happening with that mechanism. Okay, just if we put that into Grubler's equation, number of binary links is 1. If you've got 2 connections here, or if you put it in as 3, even if you put it in as 3, still doesn't work. That would give you 0, right? So doesn't work the way Kutzbach's criterion does for open linkages. Right? Okay, so we've got now 2 6-bar mechanisms, right, with different configurations. What's the difference? Right, the only difference is that we've got the placement of this link here. Right? So here we've got it between the 2 ternary links. All right. So let's see if we can work out what the mobility of this 6-bar linkage is. Right, so do the same thing again, count the number of links, including ground, number of 1 degree of freedom joints, number of 2 degree of freedom joints. I'll let you do that while I put my mechanisms back together again. Okay. Okay, so hopefully you counted the number of links, including ground, to be 6, and the name gives it away, of course. Count the number of joints. So we've got 7. So let's see here, 1, 2, 3, 4, 5, 6, 7. No half joints. What's the mobility? 1. Okay, so still, even though it's a 6-bar linkage, because we've got these two ternary links in here, the mobility is still only 1. Right? So previously we had a 5-bar linkage and it required, I had a mobility of 2. This time we've got a 6-bar linkage, but a mobility of only 1 because 2 of the links are ternary links. Right? So if you do Grubler's equation, number of binary links, we've got how many? 4, including ground. How many? So the other 2 links here, links 3 and 6, are ternary links, right? 3 nodes, so we don't count those. And then we've got no 4 or 5 node links. Put that into Grubler's equation, and we get a mobility of 1. Okay. And we can do the same thing again for the Stevenson 6-bar linkage. Okay. So I'll leave you to do that. All right, hopefully you've had a go at that. I left blanks in the lecture notes for you to have a go. So I'm just going to put the numbers up this time and show you that it's mobility of 1 for both. I recommend that you have a go at building this in SolidWorks and just to see how it moves. Okay, so nearly finished. So the last thing we want to look at is categorizing 4-bar mechanisms, right? So typically 4-bar mechanisms are the most common and most useful of the mechanisms that you'll make use of. The other one being a crank slider mechanism, which is actually a special case of the 4-bar linkage. But anyway, so what we want to know about our 4-bar mechanisms often is whether it's a crank rocker or just a rocker. So for example, if you look at the little video of me in the side, we might want to rotate this short link all the way around and have this output link just rock back and forwards. Right, so we need to know whether it can do that. So because of the interference of the nuts and bolts on here, I can't actually make this rotate all the way around. But I think hopefully you can see that if there wasn't that interference, that I could rotate that around, right? Because there's room left for this to go more horizontal. Yeah. All right, but if you wanted to do some calculations to work it out, you can use Grashoff's equation or Grashoff's criterion, which says if you've got a 4-bar linkage, if you do the sum of the length of the shortest and longest links and compare that with the length or the sum of the lengths of the other 2 links, if this relationship is true, then at least one link will rotate through 360 degrees, okay, relative to the others, right? So if this is true, then you know that at least one link can be a crank. If it's not true, then no links can rotate through 360 degrees and the linkage will be a triple rocker, right? So all links will just rock. apart from the ground link, of course. Right? So depending on which one we treat as the ground link. Right, so this one you can see, right, is only going to be, if we hold it this way, can only be a triple rocker, right? Because this one can't get any. So if I hold it this way, right, if I get it horizontal, you can't get any longer this way for this thing to be able to rotate around, right? Or this thing to be able to rotate around. Right? So if this relationship is equal, then all inversions are either double crank or crank rocker. So what we mean by an inversion is what I was doing here by changing which is the ground link. Right? So that's all that means, right? So it's the same mechanism. So if you're looking at me in the little video on the side, right, that's one inversion. If I make this short link the ground link, then that's another inversion. If I make this link the ground, then this is another inversion. Okay, so that's just the terminology, the mechanism's terminology that we use for doing that, right? Changing where you hold changing what link is the ground link. All right, so if Grashoff's equation is true, right? So at least one link can be a crank. Then depending on where the shortest link is located, so depending on the inversion, the 4-bar linkage will be as follows. Right. So if we make the shortest link, which is this one here, in my little mechanism, make that the ground, it becomes a crank. Right. So, and we saw that before, right? So here, in order for this part to become horizontal, in order for it to rotate around, this needs to get longer, right? So this one's a crank. If we have a crank rocker, if the shortest link is the input link, right? So shortest link is now the input link. So I can, without the interference of the nuts and bolts, right, I would be able to rotate that around. So this link over here, the shortest link, would be able to rotate 360 degrees, and this output link here would just rock backwards and forwards. Okay. Will be double rocker if S is the coupler link. So that's this shortest link is the coupler link. So that's this one here. All right. So that's rocker. We can't do anything with that. All right. And if S is the output link, which is this one here, it's a rocker crank, right? Which makes sense, right? It's just the opposite of this. Actually, just thinking back to what I said about this one here, I think I got that wrong, didn't I? So S is the ground link, right? Yeah, so this one out here can rotate around 360 degrees because there's still room for this to move. Yeah. And that can go all the way around. Right? So it will look like something like this. All right, if you wanted to do the calculations, just to check, so this is, and we did this in the classroom, 1, 2, 3. This is 1, 2, 3, 4. And this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we've got the shortest link is 3. The longest link is 5, so that's 8. And then the other two links, we've got 4 and 5, so that's 9. Right, so 8 is less than 9. So for this mechanism, Grashoff's equation is true. Okay, no, we're not going to do that this time. So that's the end of the lecture, 46 minutes or so, a little bit long. But that's about how long we took to go through through it in class. So if you didn't go to class, I covered pretty much everything we did in class, apart from a bit more discussion about various things and showing my SolidWorks models. and getting to see this a little bit more clearly. Right? All right, so that's it for now. See you next time. Hope you enjoyed the subject and learned something from it, and found it interesting. And good luck with your career if this is your last subject. I know for some of you it is. Yeah, all right. Bye for now.